Hello, students. Today we're going to tackle a topic that sometimes gives us a little bit of trouble, numericals on defects of vision. But don't you worry, because by the end of this session, you're going to feel so much more confident solving them. So let's begin. Now, I want to tell you something really important. The biggest mistake that most students make when they're solving these numericals, well, it isn't in the calculation. It's not about messing up the lens formula, believe it or not. So what is it then? The most common error, the one that causes you to lose all your marks, is choosing the incorrect type of lens right at the very beginning. That's right. Understanding the concept is so much more important than just putting numbers into a formula. Think about it. If you pick the wrong lens right at the start, then your focal length will be wrong, the sign will be wrong, and your final answer for power, poof, it's all gone. So how do we make sure we get it right every single time? Well, we're going to become detectives. Every single question has clues hidden inside it. You just need to know what to look for. So whenever you get a question, you need to ask yourself just two simple things. First, what is the person having trouble seeing? Is it things far away or things close by? And second, what can they see perfectly fine without any strain? This is your key to unlocking the whole problem. All right, let's jump into our first case study, myopia. You probably know it as nearsightedness. This is the condition where things far away look all blurry. So, just like the definition says, if a person has myopia, they can read a book up close just fine. But if they're trying to see the blackboard from the back of the classroom, everything is blurry. Now, this is so interesting. Look at what's actually happening inside the eye. The eye's lens is just too powerful, you know? It's bending the light rays too much. So the image of a distant object is forming in front of the retina instead of right on it. That's what's causing the blur. So our job is to use a special lens that tricks the eye. It takes a faraway object, one that's at infinity, and it creates a virtual image right at the person's own far point. That's the furthest distance they can see clearly. This lets their eye focus on that image properly. And here is the magic solution. Remember how the eye was bending the light too much? Well, to fix that, we need a lens that does the opposite. We need a diverging lens. A concave lens spreads out the light rays just a little bit before they enter the eye, pushing that final image back onto the retina where it belongs. So let's make a quick checklist for myopia. The defect is blurry distance vision. The lens type you need is concave. And this is super important. For a concave lens, your focal length and your power will always be negative. Remember that. All right, are you ready for our second case? Let's talk about hypermetropia, or as you might know it, farsightedness. This is the exact opposite problem, where nearby objects are blurry. So this time, the person can see the mountains far away perfectly clearly, but when they try to read the newspaper, oh, the words are all jumbled up and out of focus. See what's happening now? It's the exact opposite of myopia. This time, the eye lens is a bit weak. It has low converging power. It isn't bending the light enough, and so the image tries to form behind the retina. So what's our mission here? We need a lens that takes a nearby object, like a book at the normal reading distance of 25 centimeters, and it forms a virtual image at the person's actual near point, which might be, say, a whole meter away. So if the eye isn't bending the light enough, we just need to give it a little help. And the perfect lens for that job is a converging lens, a convex lens. It helps bend the light rays inward, allowing the eye to form a sharp, clear image right on the retina. And here's our checklist for hypermetropia. Easy to remember. The defect is blurry near vision. The lens type is convex, and for a convex lens, the focal length and the power are always positive. See? It's the exact opposite of myopia. Now, before we wrap this up, I have a very crucial reminder for all of you. This is where silly mistakes happen and you can lose marks, so please listen carefully. It seems simple, I know, but please always remember, 1 meter is 100 centimeters. Questions will often give you distances in centimeters. But, and this is a big but, to calculate the power of the lens in diopters, the focal length must, I repeat, must be in meters. Always double-check your units before you use the formula P equals 1 by F. And please remember this, the sign convention is not a random guess. You don't just pick plus or minus. It comes directly from the type of lens you choose. Once you correctly identify the defect as myopia, you know you need a concave lens, so you know the power has to be negative. It's all connected logically. Okay, so after all of this, I want to give you a simple golden rule that you can carry with you right into the exam hall. This is your final takeaway. Just burn this into your memory. If the question says blurred distance, you think myopia, which means you need a concave lens, which means the power is negative. Got it? Now, if the question says blurred near, you think hypermetropia, which means you need a convex lens, which means the power is positive. That's it. That's the whole game right there. By focusing on the concept first, you really can master these numericals. The next time you see one of these problems, please don't panic. Just remember to be a detective, find the clues, and choose the right lens. I really hope this helped you all. All the very best.